This term contains del x phi square, del y phi square, and del z phi square. So therefore, the partial derivative with respect to del z phi will throw up a twice del z phi, which will, the twice factor will cancel with the half factor outside, and then there is another del z which is outside, so it will convert it into a del 2 phi del z square. Okay, first derivative of del Lagrangian with del z phi will give you twice of del z phi with two factor that cancels out, and therefore I have a double derivative of phi. Similarly for y, I will get a double derivative of phi with respect to y, and for from x, again I will get a double derivative of phi from x. So remember, there are three terms: del x phi square, del y phi square, del z phi square, and the operations these, the spatial operations give you the double derivative terms. All of them will come up with a minus sign because there is a minus sign outside, and all of them will come with a factor ch square. So all these things came with a factor ch square, and this also had a factor ch square. So what I can do, I can throw away all the ch squares on the right hand side, and it will become 0 to the zeros side. So I can just write the operational part, which are just made from the phi's and their derivatives. So from the first term, I am getting the double derivative with respect to double derivative with respect to ct with a positive sign, and then the three terms which are double derivative with respect to spatial coordinates, which come with a negative signs. And lastly, I would have a plus m square c square phi h square. The plus sign came from the two minuses, and ch square I have thrown outside. This was a 2 phi, and this 2 and this 2 cancelled out each other. Okay, so ultimately you see that irrespective of the overall constants here, overall constants in equations of motions do not matter. They do matter at the level of getting the conjugate momenta, as we will see, but at the equations of motion level, overall constant do not matter. And indeed, from the Lagrangian which we started with, we end up getting the Klein-Gordon equation, and that is what we were looking for. So we have identified a Lagrangian from which Klein-Gordon equations can be obtained, and now I can do the business of going to phase space with this Lagrangian and quantize the theory. I have not told how did I get this Lagrangian, I just told that it is the Lagrangian which does the job for us. So in this course, we are not going to discuss about how to obtain a valid and good Lagrangians for theory, but you can pay attention to the fact that the Lagrangian which I have written, you can see that c and h bar square over here and here are fundamental constants. This operation here, del t phi square with a minus sign, del x phi square, del y phi square, del z phi square, together, remember, this is an invariant operator, invariant action on phi. Mc square, phi square, h square is also invariant object. So it so happens that the whole Lagrangian is also invariant under Lorentz transformations. So therefore, in order to get a relativistic theory of phi fields, we should write a Lagrangian which is compatible with the symmetries which we are seeking for, namely the Lorentz transformation. So in this Lagrangian, I have just made certain that I write down the Lagrangian which is consistent with the Lorentz symmetries. Is this the only Lagrangian which is consistent with the Lorentz symmetries? It is not. There are other many, infinitely many Lagrangians. This in some sense, is a simple most Lagrangian which you could obtain. There are other complicated Lagrangians, but they would be talking about quantizations or Lagrangians or equations of motion for all other complicated fields. Here, the Klein-Gordon equation in some sense is depicting the motion of a quantum particle which is relativistic. It is a free particle. There is no potential in this game. So only the mass and the derivatives, which are the kinetic terms, are appearing. No potential is appearing. So in that sense, it is trying to depict the dynamics of a simple enough system, most simple system as you can visualize. Therefore, the Lagrangian which is there is also most simple, relativistically compatible Lagrangian. Okay, so the philosophy is typically to write down a Lagrangian which is consistent with the symmetries, and then look for various orders of complexities. Since we are looking for simple enough systems to be described with, I have written a Lagrangian which is simple most in that setting. Okay, fine. So given that the Lagrangian is known to us now, which gives rise to the equations of motion, now it is the time to go to the phase space of this Lagrangian and try to obtain the Hamiltonian and try to quantize the system. All right. So in order to go to the phase space, what we have to do, we have to take one of the derivatives and trade it with the momenta. So typically the time derivative is traded. So we are going to trade with del 0 phi. Time derivative is just scale with c, such that del of phi upon del ct we will do. So therefore this time the conjugate momenta will be defined like this. I am trying to trade off del 0 phi with pi. Okay, previously we used to trade off del t of q with p. So the same game is there up to relativistic version. There is a c, and that's what I'm going to trade for. So first I obtain the conjugate momenta corresponding to phi, which will be identified as del L of del 0 phi. So again, in the Lagrangian density, we will search for where is del 0 phi. So remember here, this term 1 over c square del t phi square can also be written as del 0 phi whole square. And when I take the derivative with respect to del 0 phi, this term will only come into the picture, and its derivative will give me twice of del 0 phi. And outside there is a minus ch square, and inside there is a minus, overall a plus sign. And outside also there is a twice factor which is in the downstairs, and ch square which is outside. So ultimately I'm getting ch square del 0 phi. So that's what I should get, ch square del 0 phi. And remember that del 0 is del phi upon del ct. So c here and c hiding in the del 0's definition cancel each other, and I have just h square times phi dot. This dot is derivative with respect to time and not with respect to ct. C has been cancelled. All right. So now we have the field, its conjugate momenta at hand, and the Lagrangian we have identified. We can go to the Hamiltonian and the phase space as we do in classical mechanics as well. So Hamiltonian in classical mechanics is obtained from qp dot minus the Lagrangian. So q dot p, sorry, not qp dot, q dot p or pq dot minus l. Okay, so p is the quantity you are trying to obtain as a new variable in the place of q dot. This is what it is being traded for. So Hamiltonian will be a function of q and p. Lagrangian was a function of q and q dot. So q dot is being replaced by the new quantity p. Similarly, for fields, del 0 phi is trying to get replaced, and it is trying to get replaced by pi. So pi del 0 phi minus Lagrangian density. That's what we would have. So again, remember the momenta pi was h square phi dot. So I will write pi as h square phi dot, and del 0 phi is phi dot upon c. Okay, this would be phi dot upon c. So effectively you will get h square by c times phi dot square, which I have written in a funny way, c times h square divided by c square, which will just give you h bar square times c and phi dot square, and minus the Lagrangian. Okay, so far so good. Let me just clean it up so that we can clearly see what we are headed to. So secondly, minus Lagrangian. So Lagrangian is coming with its own phi dot square. So remember, Lagrangian has minus hc square by 2 and minus 1 upon c square phi dot square. And there is special derivative which I will come to in a minute. But you see, Lagrangian itself is coming with hc square divided by c square phi dot square. Okay, so sorry, so not hc square, h square c here outside, sorry, I'm making h square c here. So you see the similar kind of term which is appearing here is also coming from the Lagrangian, but with a half factor. This term that did not have a half factor, this has a half factor. So they will subtract out, and only half of this term will survive. So that is what it is here. Half of first term will survive because another half is coming from the Lagrangian, which will partially cancel it. Now, what about the spatial derivatives? Spatial derivatives from here, for example, we are coming with all the spatial derivatives were there. Del x phi squared, del y phi squared. They will just come with negative signs in the Lagrangian with a h square c by 2 factor, and under minus L they will become positive signs. So you will get a half of all the spatial derivatives squared, the gradient squared. Lastly, there was a minus, so there was a inside, uh, yeah, so overall in the Lagrangian, if you look at, there was minus mc square, m square c square upon h square, phi square was there overall, with a plus sign rather, and then effectively with the Lagrangians outside minus, there was this minus sign here, and minus L will convert into a plus. So just let me have a look at once more. In the yeah, so effectively this should have been a plus only. Let me see. They should have been a plus. All the things have the same sign over here. So minus k square, and here I should get a minus ch square. Yeah, so it should have been a plus over here. Fine. So therefore, overall you will get a plus from here. So you will get total Lagrangian is subtracted out. What it does, it makes it half of its value, and the spatial derivatives comes with positive sign, and the mass term comes with a positive sign, and ultimately you have this as your Hamiltonian. You see, Hamiltonian is made up of ch square, then half of the temporal derivative square, half of the spatial derivative square, and the phi square with mass square, h square, and h bar square. So which can compactly be written as a last term over here. Remember, phi dot was what? Pi upon h square. So phi dot was pi upon h square. So game of going to phase space is complete when you jump to the variable in the phase space. So phi dot will be replaced by pi upon h square. So this quantity here, which is appearing, okay, is nothing but yeah. So it is nothing but pi upon h square to the power 2. So pi square upon h4. Okay, pi square upon h4, and there was a c square which I have probably missed out, which is this c square. Okay, so this is your Hamiltonian. You can see the Hamiltonian is made up of only squared quantity. This is pi square upon c square h4. This is Laplacian of phi square, and then m square c square phi square h square. So this is the Hamiltonian, which is positive semi-definite. There is no quantity which is single power or odd power, or no quantity which is coming with negative sign. So ultimately your Hamiltonian therefore is a positive definite quantity, at least at the classical level. What it does at the quantum level, we will see in a minute. Hopefully this will remain so, because at the quantum level, just like Q and P were converted into operators which were Hermitian, pi and phi and its derivatives can also be converted into Hermitian operators, and square of Hermitian operators gives you positive eigenvalues. Okay, so squared Hermitian operators have positive eigenvalues. So none of these quantities are supposed to be negative. So that's why by going to quantum level, at least we have solved the problem of negative energy in some sense. Hamiltonian has become positive definite quantity. Let us go and see if at the quantum level we are able to see the same thing in more realistic sense in the dealing with when we operatorize it, whether this retains the structure or not. Okay, so let us first rewrite the Hamiltonian in order to see it neatly. That Hamiltonian is this hc square h bar by c times h bar square upon 2, and then there will be 1 over c square pi square upon h to the power 4, and gradient of phi squared plus m square c square upon h bar square phi square. That would be the structure which we will get. Okay, so now let us go back and try to operatorize that. As far as we have discussed, everything looks consistent until the classical advent, because You see, all these quantities are positive semi-definite. We want to see if something similar kind of thing remains true at the quantum level as well or not. Then at least Hamiltonian's energy remaining positive condition would be obtained, and then we will see whether we are stuck with the same problems or not. So let us go ahead. So remember, we had the Klein-Gordon equation which we wanted to operatorize. So we do that. We make the phi's appearing in the Klein-Gordon equations as space-time dependent operators. So phi is a function of x and t. That means at each x and t, I would have some operator which will satisfy this equation. Since I have an operator at all positions, and I know any function of position can be done a Fourier transform with respect to momentum k's, which is to say, if I know a function fx, I can obtain it from superposition of e to the power ikx with weight factor fk. So you see the integration is over dk, and e to the power ikx I put, and then f of k is the weightage. Which k modes comes with how much weightage is decided by fk, and together they constitute f of x. Similarly, the same thing will be happening for phi x of t, where phi is a function of x and t both. Out of that, the x part I am trying to expand in the plane wave basis, e to the power ikx, and weight factor phi of k comma t, because phi is also left hand side the position space time dependent is. Out of that position part, I am doing a transaction with respect to the plane waves and integrating over the k modes. So therefore, the spatial part, the space dependency, x dependency, is captured by e to the power ikx integrated over all possible k's, and the time dependency is captured by this phi k of t. So this is how a superposition I am proposing that exists to write down the operator from the position space to Fourier space. That means how many different operators at momenta k, this should be a vector k, momenta k, constitute with a weightage e to the power ikx an operator at location x. So at one location x, this is space location x, there are different k's, k1, k2, k3, all of them combined to give you one operator at x. This is the essence. So position operator at a position is a superposition of positions at different wavelengths, different momenta, and sum over with the plane wave weightage. Okay, if that is the case, then I should do the Laplacian and the time derivative which appears in this box operator. Okay, so remember, when I do the Laplacian hides three double derivatives in it. Double derivative with respect to x, double derivative with respect to y, and double derivative with respect to z. So for instance, let us say if I act upon the double derivative of with respect to x on phi, the double derivative will search for x dependency. X dependency is only in the exponential. So therefore, the exponential function will undergo the double derivative with respect to x, and you will get a minus kx square. Minus because iota will come down twice under double derivative, and you will get a minus kx square. Similarly, when I do the double derivative with respect to y, you will get a minus ky square and the exponential function back. The whole thing will be back to itself with addition of minus kx square for the double derivative of with respect to x, or minus ky square if you have a double derivative with respect to y, or minus kz square if you are taking the double derivative with respect to z. And when you add them all together, you will get a minus of kx square, minus of ky square, minus of kz square, which is equivalent to minus of the vector k mod square, meaning the magnitude of the vector k square with a negative sign will appear, and the whole function will come back to itself. Okay, so under the Laplacian action, only the exponential part is hit upon, and therefore you earn a minus k square inside the integral. Similarly, this box operator hides a double derivative with respect to time as well. So time part is only present in the phi of kt. There is no time dependent in exponential, neither in k's. So therefore, the double derivative with respect to time will only hit this part, del 2 phi upon del t square. And remember, the definition of box was minus 1 over c square del 2 upon del t square and plus Laplacian. So this Laplacian will give you minus k square. This double derivative of with respect to time you give you del 2 phi upon del t square, or phi double dot square with a minus sign, and this will give you a minus m square c square h square. So ultimately, if you write down the whole thing in expanded basis, you will get, so Let me open it up. You will get ultimately with a minus sign integration of d3k and phi of k, integration of d3k, sorry, phi of k double dot coming from the double derivative of phi with respect to time, plus k square, which is kx square plus ky square plus kz square, plus m square c square upon h square, and this both the terms are coming with phi k, and then e to the power I k dot x is equal to 0. So the Klein-Gordon equation, when opened up in the Fourier basis, becomes this equation. Of course, again, if this equation has to be holding, it has to hold true, then since e to the power I k x cannot take value 0, under integration you want this to become 0 for all possible phi k's which you can think about. This can only happen if your, again, the integrand's first fraction goes to 0. That is to say, phi double dot plus k square c square. So actually you will get a k square c square here and m to the power c4. Why you will get? Because the box operator had a 1 over c square as well, if you remember. I wanted a 1 over c square. That c square, if I take away from here, actually it was c square like this, which I multiplied throughout the equation. On the right hand side, since it is 0, I can multiply with c square. You can work it out, you will get that. So ultimately you will get phi double dot plus k square c square plus m square c to the power 4 upon h square, and then together multiplying the phi k of t. And all of these things are operators, let us say. Okay. So now you see you have an equation like phi double dot plus something times phi. Let us call that something as a omega k square. Omega k square is this combination. You see this combination is just made from real number k, real number c, m, c, h bar, everything is real number. So this is just a real number. So you have an equation like some operators double dot plus omega k square, and that operator is equal to 0. Compare it with the harmonic oscillator operator equation, x double dot plus omega square x operator was supposed to be 0. So therefore the phi k's, here should be a label k, let me write it down. The phi k's, the phi k which are appearing here, I am calling it a subscript k because I don't want to write phi comma k and t all the time. So this is same as phi k. Either you write it in expanded version like phi k comma t or just phi subscript k. So you see these things which are appearing over here, they satisfy an operator equation which is exactly like harmonic oscillator equation, operator equation. Okay, and from there these operators, you know, you have to just combine them with plane waves to get the operator in position space. So we are after a position of space operator. The trick we played that we will write down first in momentum space operator, and those momentum space operators combined together with plane waves generate for me the physical space operator phi x of t. And crucial thing about this is that this phi k of t, these new set of operators in momentum space, behave as oscillators. So each phi k of t, when I tried this, I demanded that this equation should be true for all k. Here also I demanded this equation, the integrand of this should vanish for all k's. So it looks like all of the phi kt's together generate phi of x of comma t, but also this all of phi k of t satisfy harmonic oscillator equations. So therefore the real field which we are looking after is a peculiar combination of harmonic oscillators times some plane wave and integration over the frequency of all the oscillators summed over. Meaning d3k is, you can think of a different oscillators being summed over with weight factor e to the power ikx. So therefore the field which we are really wanting to learn about, the quantum field, is a set of oscillators in momentum space. It is not that in real space there are tiny oscillators. Do not confuse it with that analogy. Typically sometimes you will hear that field is like oscillators. They are oscillators in momentum space, in an adjoint space of x. These operators live, which we do not have ready access to, but we know together they combine in a particular fashion to generate an operator at location xt.